So, we have been discussing about the wave propagation solution of systems governed by systems in one dimension governed by the wave equation. So, we have looked in one of the previous lectures that the solution of the wave equation can be written in terms of the general solution of the wave equation can be written in terms of these propagating waves, one in the positive x direction, other in the negative x direction. So, let us say that we have a positive travelling pulse. So, a positive travelling pulse is represented by this pulse travels as time progresses, this pulse travels in the positive direction. At a speed c. So, let us look at this form of the pulse f z. Now, we know from the theory of Fourier transforms that a pulse of this form may be represented in terms of the Fourier integral So, this we call the Fourier integral. So, a pulse like this may be represented in terms of as a I mean this integral you can see you can interpret this integral as a superposition of harmonic pulses. This can be written in terms of cosine and sine of k z. So, therefore, any pulse like this is a superposition of sines and cosines and represented in terms of this integral, where this k is known as the wave number and lambda is the wavelength. So, if you consider an example, simple example, suppose f k is nothing but say pi times delta So, if you consider it like this, and this let us say you have plus So, f k this is a function of the wave number So, these are Dirac delta functions or distributions represented with this arrow. So, if you substitute in here, now when you have the Dirac delta at A, so k gets replaced by A and this pi, therefore, what you have here, it gets replaced by minus of A and this is nothing but cosine A z. So, if you want to have a propagating cosine pulse or cosine wave, so this is the representation and by so this is, you can say, the spectrum of the cosine function. So, in the Fourier space, like this you can represent different kinds of functions and therefore, you can correspondingly find their propagating representation by replacing this variable by x minus c t or x plus c t, as the case might be. So, finally, what we understand by this integral is that we can consider any wave pulse as a superposition of harmonic waves. So, these are superposition of harmonic waves. Now, since we are dealing with linear systems, superposition of harmonic waves, if that represents a pulse, therefore, if we study the propagation of a harmonic wave, then we can equivalently construct our the propagation of our pulse by just summing up or superposing all these harmonic individual harmonic waves. So, our problem is somewhat simplified, that we do not have to deal with complex wave forms if we can study the propagation of a wave of this form So, W, so this is maybe this I will call f. So, this is we will actually represent this as where omega is the frequency. Now, we will see how this comes about. So, we can write So, this is a superposition of propagating harmonic waves. and what we are going to do is, as I just now indicated, we are going to write it like this. So, here k is the wave number, omega is the circular frequency. Now, why this? So, this is k x and k c I am writing as omega. So, how do I come to this form? So, if you substitute this solution form in the wave equation, then you see that this choice of k c equal to omega satisfies the wave equation. So, and if I substitute this solution form, then I will have, so this is double derivative with respect to time. So, this is minus omega square, and here there is a double derivative with respect to space, that will give minus k square. So, this will be plus c square k square. So, that will imply so the relation between the circular frequency of the wave and the wave number is given by this relation. This relation is known as the dispersion relation. So, this is known as the dispersion relation. So, it is a relation between the circular frequency of the wave and the wave number. Now, this dispersion relation is a property of the medium. Say for example, in the case of a string, this is the dispersion relation, but later on, as when we will discuss beams, we will find that the dispersion relation is different. So, this dispersion relation characterizes a medium or a material. So, a dispersion relation which is such that omega over k is a constant, is not a function of k or omega, is known as a non-dispersive medium. So, what is this I mean physical significance of this dispersion relation? So, let us understand briefly. So, so what we have is an infinite system of infinite extent, let us say a string or a bar which is of infinite extent, and there is a propagation of a harmonic wave in the string or the bar, in the medium, as we will commonly call this. So, when a harmonic wave propagates, a harmonic wave is associated with a wave number and a frequency. So, wave number is related to the length of the wave, the wavelength. So, let us say suppose this is the wave that is propagating. So, this is the wave that is propagating. So, there is a definite length lambda and 2 pi over lambda is the wave number, and there is a definite frequency associated. So, if you look at a particular point of the medium, let us say this point, then the point of the medium is oscillating at this location as the wave moves. So, there is a definite frequency associated with this oscillation. So, these are the two things that are associated with a propagating harmonic wave. Now, what the dispersion relation tells us that these two cannot be independent, these two cannot be independent. So, the wave number, the wavelength and the frequency of the wave, they are related, and that relation is a property of the medium. So, the medium decides what should be the relation between the wave number and the frequency of a travelling harmonic wave. Now, if this relation is such that this omega over k, as you see here, is a constant, it is not a function of either omega or k, as you have here, then the medium is known as a non-dispersive medium. Now, let us understand what is dispersion briefly. So, you see this c, as you know, is the speed of propagation of this harmonic wave or any wave pulse in the kind of medium that we are discussing, which are governed by the wave equation. So, the media which are governed by the wave equation are all non-dispersive media. Now, in that c represents the speed of the wave. So, if I look at this crest, the speed at which this crest moves. Now, if that is independent of the wavelength or the frequency, then something interesting happens. So, what happens is all waves, that means waves of all wavelengths, as I have discussed, that a general pulse can be thought of as a superposition of harmonic waves of different wave number. This is a superposition of harmonic waves of different wave number, which means it is a superposition of harmonic waves of different frequency as well, because frequency and wave number are related for a median. So, all these waves of different wave numbers, they are travelling at the same speed, it is independent of the wave number or the frequency. So, they are all travelling at the same speed, therefore, what happens is a wave pulse that has a certain shape at this point, as it moves it retains its shape. So, as time progresses and as the pulse moves, it retains its shape, because all waves that are superposing to produce this pulse, they are all moving together. But in a non-dispersive medium, this does not happen. Some waves of certain wavelengths or wave number, they travel at different speeds than harmonic waves of another wave number or another wavelength. So, what happens is this pulse loses its shape. So, it possibly flattens out as it moves. So, in a non-dispersive medium, the pulse or the wave form, it retains its shape as it moves. In a dispersive medium, it will lose its shape. Now, air is a non-dispersive medium. So, what I am speaking, the sound that I am producing is reaching you with no distortion. Had it been a dispersive medium, then it would have been very different. So, that is dispersion. So, what we will be discussing or restricting ourselves to is non-dispersive medium for the moment. Now, we have so this speed c, that which is the ratio of the frequency of the harmonic wave and the wave number, is the wave speed. As we have seen, we qualify it a little further, we call it the phase speed. And we will come across another speed as we progress in our discussions when we come to dispersive medium. So, this is the phase velocity or phase speed. Now, the next important thing that we are going to discuss is wave impedance of a medium. So, when we want to set up a harmonic wave, So, now we will be always talking in terms of harmonic waves. When we want to set up a harmonic wave in a medium, let us say a string, you have a taut string and you want to produce a disturbance or a wave in that string, a harmonic wave in that string. So, you will take one end of the string which may be connected at a distance, the other end is connected at a distance, and you produce a wave. You will be met with a resistance. The medium or the string will resist this disturbance. Why it will resist? Because you are going to pump in kinetic and potential energy. So, you must do work. So, there must be a resistance to this motion. So, this resistance is resistance to setting up of this harmonic wave. This we roughly term as impedance. We will make the exact definition as we proceed. So, impedance is the resistance offered by a medium to setting up of harmonic waves in a medium. So, that we will call as the wave impedance of a medium. So, this is the resistance to setting up of a harmonic wave. And mathematically this is written in terms of so impedance is denoted as Z is the ratio of the complex force amplitude part divided by the complex velocity. So, remember that we are discussing everything in terms of complex representations. So, we will represent this everything, say force, velocity, everything in terms of complex numbers. So, to take an example, let us consider a string So, suppose you have a semi infinite string. So, this other boundary is far off, which we idealize as infinity. So, the other boundary where it is fixed is at infinity. There is tension in the string, and this end, which is a frictionless sliding end, is being forced with a harmonic force, let us say. So, this force must be equal to, written in terms of the tension in the string So, this force must be equal to negative of tension times the slope at 0. So, this is x and if you consider that this a harmonic wave propagating with amplitude b propagating in the. So, what you set up is a positive travelling wave. I mean this is obvious because as you disturb, the disturbance is going to move to the right. So, you set up a positive propagating wave, and since there is no other boundary and no other disturbance source at infinity or anywhere in the string other than this point, there will not be any negative travelling wave. So, there is only a positive travelling harmonic wave set up in the string, and this will be true if of course, there are no defects or no inclusions, no mass elements etcetera in the string. So, this string is uniform. So, this therefore, if you substitute this solution, what you obtain is so I have put x equal to 0. So, that is the force. Now, the velocity at x equal to 0 is given by so, the complex force amplitude is this part and the complex velocity amplitude is this. So, we define impedance as now omega over k is the phase speed, the speed of harmonic wave in the string, and using the definition of speed once again. So, you see c is or c square is T over rho a for the string. So, I will replace this tension in terms of density and area of cross section of the string. So, that will give us. So, that is the impedance of a string. Now, similarly, if you consider a bar, a semi infinite bar, to which you apply a force, a harmonic force, so from the boundary condition so when you apply a harmonic force here, you assume that harmonic waves are set up in the bar, which can be represented as this. So, this is the so you have positive travelling harmonic waves in the bar, and this turns out to be putting x equal to 0, and similarly you can write the velocity once again. So, here I have a negative sign, and here also I have this sign. So, this is the complex force amplitude, this is the complex velocity amplitude. Therefore, once again I can define the impedance of a semi infinite bar as E A. Once again omega over k is c, and E A can be the speed of waves in a bar, can be written like this. So, what we have is, so I eliminate this E as rho times c square, and here I have the impedance of a bar. Now, in the case of a bar, this is axial waves, and these are essentially pressure or stress waves, and you can define what is known as the specific impedance. So, specific impedance is this impedance over area. So, it is impedance per unit area. So, this is a ratio of the complex stress amplitude divided by the velocity amplitude. So, this is in terms of stress. Now, in the two cases that we have studied, this impedance appears as a real number. These are real quantities, but in general impedance can be complex. It is a complex number and dependent on. So, this is complex, and it can be a function of frequency. So, in general it can be complex, and it can be a function of frequency. Now, as I mentioned that when you disturb a string, so if you take a semi infinite string and the free end, which is a sliding end, you disturb it, you give a harmonic wave, what you will be setting up is a travelling harmonic wave. Now, as I said that you will feel a resistance when you want to set up these harmonic waves. So, why do we have this resistance? Because there was some undisturbed string, we are pumping in energy. We are pumping in energy into those parts of the string. So, as I start moving, as you have seen that far end of the string may be still undisturbed. So, and when the disturbance reaches this part, the point up to which the disturbance has reached, up to that part the string has kinetic and potential energy. So, you see I am pumping in energy into the string, and this energy is therefore flowing as the disturbance propagates in the string. So, this wave, the harmonic wave, must be carrying energy. A travelling harmonic wave must be carrying energy with it in order to disturb the yet undisturbed regions or portions of the string. So, let us try to calculate this flow of energy or the power that flows as you pump in or as you disturb a string. So, let us write down for a string or yeah. So, let us take the example of a string. For a string, the total energy, the energy let us say. So, now this is an infinite string or semi infinite string. Let us calculate the energy of the string. So, you have the string. Let us calculate the energy of the string in this region from x 1 to x 2. So, this consists of the kinetic energy and I have put this half common outside and this is the potential energy. So, the total mechanical energy in this region of or in this portion of the string is given by this E. Now, let us try to calculate the rate of change of energy of this portion of the string. So, once you take time derivative, so we have now to bring this expression in a convenient form, I will integrate by parts this term. So, I will integrate by parts taking this as a second function. So, then I can write, so the first function, the integral, the spatial integral of the second function and then this integral now when we do the integral of this function spatial integral. So, I will have a del w del t here and I also have a del w del t which I can take outside and there will be a negative sign and spatial derivative of this function that is what we have. Now, this being the equation of motion. So, we assume that this is being governed by the wave equation of the equation of motion of the string. So, this must be satisfied. So, this is 0. So, what we are left with is I will write this as where I have defined so the rate of change of energy of this segment of the string is given by this. So, this must have dimensions of power. So, the time derivative of energy is power. So, this must be power. So, rate of change of energy of this portion of the string, this segment of the string must be equal to the power that comes in through x 1 into this region minus the power that leaves this region through the point x 2. So, this is nothing but the balance of energy for the string. There is no other loss like radiation or damping in this portion. So, energy must come in through this, or power must come in through this boundary at x 1 and it must leave this boundary at x 2. So, the rate of change of energy must be the amount of power that is coming in minus the amount of power that is leaving this segment of the string. This therefore is the instantaneous power flowing. So, at time t, if you look at a time instant t, then this is the expression of the instantaneous power that is flowing past the point x, any point x at that time instant t. So, this equation gives us the balance of energy. So, how the energy is change of this segment is changing with time. Suppose energy is constant, then these two must balance, that means the power coming in must balance the power going out. In that case, the energy of this portion of the string is not going to change with time. Now, let us do a little calculation for a wave. So, let this the solution or the motion of the string be given by. So, we have a positive travelling wave at in the string. So, so del w del x is given by, where this prime indicates derivative with respect to the argument. The prime represents derivative with respect to the argument. So, it is nothing but this. Similarly, del w del t is given by this expression, and therefore, this instantaneous power, the expression of instantaneous power is and this can be rewritten as writing t. So, t can be written as rho a c square now. So, that is the instantaneous power flowing past the location x at time t. Now, let us calculate the energy density of the string. So, energy density is nothing but so the total energy density of the string is given by this. So, this we integrated over the segment just a moment ago. So, this is the energy density, and if you calculate this, let us see. So, it is del W del T whole square plus this is del W del X whole square this therefore can be simplified using again this expression as now if you compare this and this, you can write the instantaneous power flowing past a location x at time t is c times the energy density at that location. So, what this so this is an important conclusion that we draw. What we can say is that the energy or the energy contained in the string in terms of the kinetic and potential energy of the string at any location x and time t is flowing at the phase speed, that means speed of the wave in the string. So, that gives us the power. So, the energy is flowing at a speed of the wave, the phase speed of the wave. Now, this is true for all dispersive media. So, for all, in all dispersive media, the energy propagates or spreads at a rate c. So, in all non-dispersive media, this this is the relation between the energy density and the power. So, the speed at which energy spreads or the energy density in the string spreads is same as the speed of propagation of waves. This might seem intuitively very clear or obvious, but the situation changes when you go to dispersive media. So, we will have some opportunity to discuss that later on in the course. Now, we have been discussing about the instantaneous power flow at any location at any time, but what is more physically or what is more useful or relevant in various situations is the average power. So, this average power, if you represent the force and the velocity normally in vibration courses, you define like this, where this force and velocity, they are real functions. So, if this is the situation, then this is the integral you perform in order to assess the average power that is flowing. And this, since we are using complex notations to denote force and velocity, this integral can be easily actually performed if you take the complex notations of force and velocity, take the complex conjugate. So, this is the complex conjugate of the complex force representation. So, normally we represent this if it is a harmonic force, and we know that from our study of discrete systems, vibration of discrete systems, that in general the velocity will have a phase difference with the force. Velocity or displacement both will have a phase difference with the force in general. In case of undamped system, this in the displacement is goes to 0 and velocity is pi by 2. So, therefore, now we have already defined our impedance. Now, impedance, as I mentioned, is a complex number. So, and the ratio of the force and the velocity is the impedance. So, the amplitude is f naught, and here it is v naught exponential minus I phi . So, this can be represented as, so the impedance can be represented like this. So, I can calculate the average power in terms of, let us say, the impedance. So, f star is f naught and the velocity I can write in terms of the impedance as and that turns out to be which you can very easily determine. You have to take the real part of this. So, that turns out to be cosine of phi. So, if z is real, then phi is like n pi. It can be 0, it can be pi, etc. So, depending on the sign. Now, if it is 0, then this impedance is positive, as you can see from this expression. If it is pi, then it is negative. So, depending on that sign, power is absorbed, or the expression of average power you can find out from here, the expression of average power. So, cos phi, power is absorbed or extracted. So, when it is positive, the power is absorbed by the medium. When it is pi, then power is extracted from the medium. This is on an average over a cycle. This is important, over a cycle. So, in parts of the cycle it may be absorbed, but and other part it may be extracted, but the overall thing is given by here. So, this is over a cycle. Now, if z is imaginary, which means phi is power cannot be absorbed or extracted from the medium. So, this is called reactive medium. So, as you can see this will be 0. So, on an average power is neither absorbed nor extracted from the medium. So, now let us look at an example. Suppose you have a mass and a spring, and this is connected to a semi infinite string under tension T. Now, as the mass oscillates, as we have calculated, the impedance of this semi infinite string is rho A C. So, that is the impedance of the string. So, once you connect this oscillator to the string, and since the impedance is real, so power will be real and positive, power is always absorbed in the medium by the string, and therefore, I can think of this system as a damped oscillator with the damping coefficient rho A c, which is the impedance of the string. So, impedance is force divided by the velocity. So, this is the damping. So, here you find that energy is being radiated out. This is an equivalent model of this system. Normally, when we draw a dashpot like this, it represents conversion of mechanical energy to thermal energy, it heats up the fluid inside. But here it is not conversion to a thermal energy, it is converted to vibrations of the string or disturbance propagating in the string. So, here the medium is absorbing the energy, and so this system is actually radiating out the energy into the medium, which is the string. So, this is an example of radiation damping. So, this example illustrates what is radiation damping, and we will discuss this phenomena later on as well. So, today we have looked at harmonic waves and propagation of energy in medium due to waves. So, with that we conclude this lecture.